Dear students, continuing with the mathematical tools of quantum mechanics, here we will discuss about function operator. Previously, we have discussed about the projection operator and Hermitian operator. Now we will discuss what is function operator. An operator f of a, that is function of an operator, it is said to be the function operator of a only if a is a linear operator. A is a linear operator, then we can write its function like we can write the function of a or f of a. And secondly, we can expand the f of a in the Tailor series, or we can do the Tailor expansion of f of a, that is summation from n is equals to 0 to infinity a power n, and here operator a power n. Now here an, it represents the expansion coefficient of this power series, that is expansion coefficient. And here now for an illustration of an operator, function operator, let's suppose we have a function operator e power a into a. Here a is just a scalar, and this can be a complex or it can be a real. So now here a is a linear operator. Now how we can expand this e power a into operator a? So we can Tailor expand this function operator, that is f of a. We can write it like summation n is equals to 0 to infinity a power n over n factorial into a power n. So here we can Tailor expand this function operator. Now we go to some properties of function operator, and one of them is let the commutator involving the function operator. That is how we can write the commutator of function operators. So for this, if an operator a, let's suppose we have an operator a, and if it commute with another operator b, if it is commuting, this commutator is equals to 0. If a commute with the b, then this operator b will commute the function of operator a. So this is the first property for the commutation relation, which involve the function operator. If operator a commute with the operator b, then function of this operator a will commute with the operator b. So first condition for the commutator a should commute with the b, then b will commute the function of this operator. Now let's f of a commute with an operator. Let's suppose if we consider function operator f of a commute with operator a, if it commute with operator a and with any other function g of a and any other function operator like g of a, we can generalize it. Let's suppose that if an operator a commute with the function of a, if it is commuting, or we can write it like a power n, and will also be the commuting with the f of a, and then we can say that f of a and will commute with any function operator g of a. So this is the second condition for the commutation involving the function operator, that is f of a can if commute with the operator a and any other function g of a. So it will commute any other function g of a like this one if a power n commute with the f of a will be equals to 0. So this was the commutation condition commuter which involved the function operator. Now we go to the Hermitian adjoint of function operator. So Hermitian adjoint of function operator. Previously, we discussed about the Hermitian adjoint of any operator. Now here we will consider that how we can take the Hermitian adjoint of the function operator. Let's suppose we have a function operator f of a, and condition for its hermiticity, we know that if any operator a is Hermitian, then its transpose should be equals to a. Now for the function operator, it is should be f conjugate of the function and then a transpose. So if it is a is Hermitian, then it means that if any operator a is Hermitian, that is its a transpose of a is equals to the operator a. If a is Hermitian, not necessarily f of a is not necessarily Hermitian, that it is not necessary for any function operator like f of a to be the Hermitian if a is Hermitian. Okay, when f of a will be Hermitian, f of a is Hermitian. Condition for the hermiticity of f of a is that f of a is Hermitian only when only when f is real, that is the function is real and a is Hermitian. A operator is also Hermitian. That is generally we know that if a transpose is a is the condition for hermiticity and a is Hermitian, then it's not necessary for the function of a to be the Hermitian. When f of a will be Hermitian, f of a is Hermitian only when function is the real and a also Hermitian. Let's suppose we take an example. Here we take the example of like e power operator a. This is the f of a, and let's suppose that it is the Hermitian. This means that f of a is equals to e a transpose, and this means that it is the Hermitian because here function is the real one and a is also the Hermitian operator because a is equals to a transpose. Here a is Hermitian and function is real, so this f of a is Hermitian. So it fulfills the condition for hermiticity. Let's take another operator and let's suppose this operator is e power iota a. Now this function is not real because it is the complex one because it involves the iota. As this function is complex one, so it is not fulfill the condition for the f of a to the Hermitian. Let's suppose that if we take e power iota a transpose, then it will be equals to e power minus iota a transpose. So here f of a transpose is not equals to a, that is f of a here, which is f of a transpose not equals to f of a. It means that it is not Hermitian. It is not Hermitian. Why it is not Hermitian? It is not Hermitian because this function is not a real one. It is the complex one. But here, in this case, this function is the real one and A is also Hermitian. So this function operator f of A is Hermitian. But here, f of A is the complex one, not a real one. So this function operator is not Hermitian, although the A is Hermitian, but function operator is not Hermitian because it's not fulfill the condition for hermiticity of the function operator, which says that f of A is Hermitian only when f is real and A is also Hermitian. Okay. Now let's we consider if A is a Hermitian operator function and which can be expanded in the form of Tailor series. Okay, f of A we can Tailor expand it like n is equals to 0 to infinity a power n, which is the expansion coefficient, into operator a power n will be Hermitian only and only if the expansion coefficient is a real one. So in the form of Tailor series, for this function operator to be the Hermitian, and condition for this that this expansion coefficient should be the real. Expansion coefficient should be the real for hermiticity of f of A. F of A will be real when this expansion coefficient is a real one, but in general f of A is not Hermitian. Okay, so if f of A, if it is not, expansion coefficient is not real, we can write f of A transpose will be equal to summation n is equals to 0 to infinity or a power n complex conjugate into a transpose power n. So in this case it is not, f of A is not Hermitian. It is not Hermitian because f of A transpose not is equals to f of A because why? Because expansion coefficient A is not real. For f of A to be the real in the Tailor expansion, it will be a real only when the coefficient A and are real. Now if it is not real, then again we can rewrite the commutator relation. So in this case, if we have learned that if A B is equals to 0, then B will commute with the function operator f of A will also be the commuting. But if A and B, these are non-commuting, that is they are not equals to 0, then in this case B will also is not commuting with the f of A. This will not also be equals to 0. So this was all about the function operator, that what is the function operator, how we can deal with the commutator involving the function operator, and how we can find the Hermitian adjoint of function operator. So thanks for watching. For more videos, please subscribe our channel.